everyone. Today we'll start the chapter 10 of class 12, that is Haloalkanes and Haloarenes. So as we know that alkyl halides and the halogenated alkanes are group of compounds derived from the alkanes. Alkanes are generalized formula is CnHn plus 2, could be methane, propane, this is ethane, propane. So these are alkanes. Haloalkanes, on the other hand, are derived from these alkanes, that is like CH3Cl, or you can see that this halogen is introduced in the formula. So these are generally commonly used as use as flame retardants. And act as fire extinguishing reagents. Also, these are used as refrigerants, propellants, and may in most common use as solvents in the laboratories. So, alkanes could be, these haloalkanes could be divided in three types: classification of haloalkanes. This classification is on the basis of type of carbon atom to which halogen atom is connected. That means if a halogen is connected to primary carbon, let's say CHH, and here halogen is connected, this one is primary carbon. If we have a secondary carbon like two R groups and one H, and to this halogen is connected, this one is secondary carbon. And if we have a tertiary carbon like three R groups are there and two halogen is to that tertiary carbon, if halogen is attached, so these are the classification on the basis of the carbon, on the type of carbon atom to halogen atom, to which halogen atom is connected. This one is primary haloalkane, this one primary haloalkane, this is secondary, and this one is tertiary. So now we'll move on to the reactions in organic chemistry generally. So before going to moving ahead, we'll discuss about the reactions in organic chemistry. Generally, in organic chemistry, we can classify reactions depending upon the reaction conditions and the reaction condition and the attack reagents. Various type of reactions can occur in organic chemistry. There are basically three types. Majorly, we can divide the organic chemistry reaction in three types. First one is addition reaction. Second one is substitution reaction. Third one is elimination reaction. So, addition reaction, what happens that a new compound is formed by the reaction of two or more compounds. Let's say here we have this. two compounds we have in the reactants as reactants, and it is generally giving us the one of the reactant is adding to the another reactant, and we are getting another product where addition of one of the reactant is happening on the other reactant. So this is an example of addition reaction where it is generally the attack of the reagent on the pi bond. So this XY is here the reagent, and it is attacking on this pi bond and making the pi this as a saturated compound from the unsaturated one. So this is one is an addition reaction. Substitution reaction, on the other hand, is that where when a functional group attacks and replaces the other functional group. For example, you have an haloalkane. Let's say you have a haloalkane with this X group, X halogen, and you are adding some other reagent Y. What will happen that this X will get replaced or substituted by Y. So this kind of reaction is known as substitution reaction, where the group which is replaced is called leaving group. This one is called leaving group. Third category, which is the elimination reaction, the reagent removes the group, for example, hydrogen or vinyl halide, vinyl halide present in the alpha beta position to form unsaturated compounds. Let's say it is the reverse of the addition reaction. So you made this XY initially. So what will happen? Some reagent will be added to the reactant, which will cause the removal of this X and Y group, and there will be formation of a pi bond, unsaturated bond will be formed, and XY will be released. So this is the like a very brief introduction to the organic chemistry reaction, which includes addition, which include which includes addition, substitution, and elimination reaction. Now we'll discuss the each of them in detail. So first talking about let's say we'll first discuss substitution reactions. So substitution reactions, what we understood from the substitution reaction, that there is this X group which will be replaced by Y group, and you will be having a Y attached and X released. This X is the leaving group, and Y will replace this X and will generate the new compound. So this substitution reactions, here this Y is act as a nucleophile. So nucleophilic substitution reactions, where the replacement of halogen atom or leaving group by the attacking of nucleophile is called nucleophilic substitution reaction. And the reaction occurs at sp3 carbon. This reaction proceeds through two mechanisms. So the substitution reaction, where a nucleophile attacks on sp3 carbon and releases a leaving group to generate a new compound. That this substitution reaction can occur in two ways. There are two kinds of substitution, nucleophilic substitution reaction. One is SN1, another one is SN2. So in SN1, what happens? Basically, there is a two-step process. It is a two-step process. So what happens is that first step involves the formation of carbocation. So you have this alkyl halide. What will happen in the first step, that this X group will be released. Since the X group is released, so there is generation of this positive carbocation, and the release of the X group generates an X minus ion. To this carbocation generated, depending upon the stability of this carbocation, the movement of these bonds may occur. So the goal is to make a stable carbocation which will favor this reaction mechanism. The rate of the reaction is depend upon the concentration of alkyl halide only here. So that's why we write this as SN1, the where 1 suggests that it is a first order reaction. Okay. Now what happens to the intermediate carbocation? Since after removal of the leaving group, there is generation of this carbocation. Rearrangement is commonly observed. Rearrangement happen in order to stabilize this carbocation. And sometimes what happens, since the carbocations form the, so the order of the carbocation stability is tertiary, secondary and primary. So if you have a mixture, if you have multiple reactions and you need to find out which one will undergo better nucleophilic first order reaction, then the one which is forming tertiary carbocation will be better one. So and the reaction is favored under protic solvents. Why protic solvents? Because protic solvents will stabilize carbocation. Now we'll discuss it in via example. It is a two-step process. So what happens? SN1, in step 1, step A, you have an alkyl halide, let's say X. Let me take one actual example like CH3, CH, CH3X. X, let's say chloride is here. So what will happen? This chloride is gonna remove, the leaving group will release. So there you will be having chloride negative ion released, and there will be formation of carbocation. So you have this secondary carbocation generated. Let's say, and then what will happen in the step 2? Here you can say, since it is a secondary carbocation and it is stable, there are no possibility of like rearrangement to form a more stable carbocation. So when in the second step, this carbocation generated, the incoming nucleophile, let's say we take a nucleophile as bromide. So what will happen, this bromide will come and attack on this carbocation, and you will be having the new product as bromide halide. So this alkyl bromide, you will be having the product. So the first step is the loss of the leaving group, and the second step is the nucleophilic attack. Let me give you two examples for the this reaction. Let's say if you have CH3, CH, H, CH, let's say you have chloride here, CH2, CH3. Okay, let's say we have one more CH3 over here. So let me just erase it. So what I am saying, let's say you have this carbocation, this halide, and the other halide that you have is uh, CH3, C, CH3, Cl, CH, H, CH3. Okay, these two halide will have the alkyl halides you have. So in the first step, what will happen? Let's say in the first case, when this leaving group is released, you will be having a carbocation generated at this position. So depending upon the stability, you can say here the carbocation generated is secondary carbocation. While if you see the other example, which is this one, if this leaving group is released, if this leaving group is released, you will be having this carbocation with CH3, CH3, positive charge, CH, H, CH3. So this one is a tertiary carbocation. Out of the two, you will see the tertiary carbocation is more stable than secondary carbocation. based on the inductive effect. I hope you guys know from the class 11 that the carbocations, the one with more number of groups attached, the one on the basis of the inductive effect, we can say the tertiary carbocation is more stable than secondary carbocation. Now, what happens in the once this carbocation generates, there is rearrangement possibility in order to stabilize the carbocation. So the rearrangements, let's say, if this hydrogen present over here, this hydrogen undergoes 1 to hydrogen shift. So what will happen? This hydrogen will come over here and the carbocation will be generated over here. So let's say there is 1 to hydrogen iodide migration, this hydrogen shift. What will happen? The carbocation will be generated over here. Now tell me, this carbocation generated is a tertiary carbocation, and the one generated over here, if it undergoes this shift, then again the generated carbocation will be CH plus CH3. This one will be a secondary carbocation. So will the shift happen in this case? No, shift will not occur. This rearrangement will not occur. While in the case, in this first case, rearrangement will occur. That will, because it will lead to the formation of more stable carbocation, and you will be surprised to see that in both the cases you will be getting only one product. In the here, if you will have the second step, which is step 2, attack of the, which is attack of nucleophile. So when bromide and nucleophile will come, it will attack on this more stable carbocation, and you will be getting this CH3, CH2, CH3, CH3, bromide as the product. And here, if you see, in this case, since there is no possible rearrangement, so the bromide will come on this side only, and you will be getting the similar product, CH3, CCH3, Br, CH2, CH3. So from here you can see, even though the reactants were different, yet the product formed is same, because there is possibility of rearrangement of the intermediate generated. So summarizing the nucleophilic substitution reaction, first order nucleophilic substitution reaction, that is SN1, what we understood, that it is a two-step process where carbocation is generated in the first process. Stability of carbocation matters. If required, there could be a rearrangement for the stability of carbocation. Out of two steps, only the first step is rate determining step. That is RDS. That's why the rate is directly proportional to the concentration of alkyl halide only. Since it is proportional to the concentration of only one of the substrate, that's why it is called first order reaction. It is favored in protic solvents. protic solvents help because protic solvents help in the stability of carbocation. Okay, and as you know, the stability of carbocation follows the order tertiary, secondary, primary. So more stable the carbocation, more will be the favorable reaction. I hope you guys understood. Now we'll move to the second uh, second type of the nucleophilic substitution reaction, that is SN2. Second order nucleophilic substitution reaction. What happens in the this reaction? It is only one step process. Instead of formation of an intermediate, there is formation of transition state. Rate of reaction depends upon alkyl halide as well as nucleophile. That's why it is depends upon the two of the reactant. That is why called second order reaction. That's why this two is written here. Okay. Now, stability of the carbocation. There is no formation of the carbocation. So rearrange also. It since it's a one step process. No rearrangement possible. Nucleophile attacks from the back or opposite side of the leaving group. So smaller the nucleophile, better will be the smaller the nucleophile, better will be the attack. So let's see the reaction. What happens? Let's say you have an alkyl halide C2H5C. You have this bromide over here. In the front, you have this C alkyl CH3 methyl group, and in the back you have a hydrogen. So what happens as a nucleophile comes? Let's say OH minus is coming, it will attack from the back of the leaving group. This bromide is a leaving group. So what happens? There is formation of one transition state in between where both the leaving group and the nucleophile are present simultaneously in the molecule, where the OH is attacking and the bromide is leaving. So you can see that both OH is attacking and the bromide is leaving, and this is happening in one transition state, one step process. Simultaneous attack and simultaneous removal of the nucleophile, and you are left with this inversion in the symmetry. So this bromide, this nucleophile attack from the back side, therefore OH comes over here and in the opposite side of the bromide, and you have this as the product along with the removed nucleophile. So there is another factor involved, that is inversion of symmetry. So what you understand from this nucleophilic substitution reaction, that it is a single step reaction. Rate of the reaction depends upon, it is a single step reaction, as you can say only one step happened. The rate depends upon both nucleophile and this alkyl halide that you used, and no intermediate is formed. Reaction proceeds through one sp3d transition. As you can see, this is a trigonal bipyramidal base, trigonal bi TBP base, so whose hybridization is sp3d base transition state is formed, where one bond breaks and another one is formed simultaneously. Rearrangement is not observed. inversion of configuration is observed. Now if you see, if you have alkyl halides, like bulky alkyl halides, there will be difficulty for the incoming nucleophile to attack. Therefore the alkyl halides, like order of the reactivity of the alkyl halides follow like this: CH3X, then primary, then secondary, then tertiary. Let me give you this example first. So if you have CH3X, this is the leaving group, this is H, and you have this nucleophile OH minus. So if this OH minus is gonna attack, since the hydrogen primary alkyl halide, no, these are small, it is easier for the nucleophile to attack. But if you have this tertiary butyl group, or you can say this phenyl groups over here, let's say you have these groups, bulky, three phenyl rings you have, and you have one halide over here, and you have this OH minus now attacking. Since due to the bulkiness of this group, there will be difficulty for the nucleophile to attack. That's why the order for the reactivity based on the alkyl halide follows this order, that this CH3X will undergo the nucleophilic substitution reaction fast as compared to primary, as compared to secondary, and as compared to the tertiary ones. As the size of the steric intense increases, so there is difficulty for the formation of transition state. Also, in the case of the SN1 reaction, you saw that carbocation forms. The carbocation is actually stabilized by protic solvents. Protic solvents will stabilize that carbocation. But in the case of SN2 reaction, there is no formation of carbocation, rather than one transition state is formed, which is not affected by the solvent or anything like that. So aprotic solvents favor this SN2 reaction mechanism. Now we'll discuss the elimination reactions and the type of elimination reactions. In the case of elimination reactions, we saw that elimination reactions are the reverse of addition reaction. Elimination reaction includes even another first other also, like substitution reaction. Elimination reactions could be divided into three parts: E1, E2, and E1C. So we'll discuss them in detail. Basically, what is an elimination reaction? Elimination reaction is that you have an alkyl halide, there will be simultaneous removal from alpha beta position to generate an unsaturated double bond, and the removal of two atoms or two groups from the alpha beta position to generate another group. So elimination reaction, the removal of the adjacent hydrogen atom and the hydrogen and the adjacent halide atom, as well as the vicinal halides, to form unsaturated compounds. As you can see, some unsaturated compound is generated, is called elimination reaction. It proceeds via three kinds of mechanism: E1, E2, and E1CB. Excuse me. So starting with E1 mechanism. Starting with the E1 mechanism. E1 mechanism, under E1 mechanism, what happens? It is a two-step process. Two-step process. The first step, first step includes the removal of. First step involves the formation of carbocations by the loss of the leaving group. So let's say you have this group R1, R3 attached, R4 over here, R1, R2, R3, and you have one H and one X. Since we're discussing haloalkane chapter, so this alkyl halide you have in the alpha position, you have this hydrogen attached. So what will happen in the first step, which is a slow step, there is formation of carbocation by loss of leaving group. Leaving group leaves first, so the X over here this alkyl halide, the leaving group X leaves and it generates a carbocation. So what happens? This will generate this carbocation H positive charge over here at this carbon with R3 and R4 groups. So this carbocation is generated. This is the first step. The second step, step 2, in it is basically the deprotonation by the nucleophilic base. Now the nucleophilic acting as a base will attack and removes the alpha proton. As you can see, there is this proton present next to this carbon atom where the carbocation is present. So what will happen? A base, nucleophilic base will come, nucleophilic base will come and that base will abstract this proton, and the two electrons of the proton will go to this single bond and making it a double bond and satisfy this positive charge. That means you will be generating a double bond over here, R3 R4, along with base and H. So this second step is a fast step. As we know that the rate determining step is RD determining, is a slow step. So the rate over here in this even mechanism, rate rate is equal to the concentration of alkyl halide only. That's why we write this 1 in the subscript over here. So the rate is proportional to the alkyl halide concentration only. Also, you observed that carbocation is generated as the intermediate. Carbocation is generated as intermediate. Rearrangement can, since carbocation is generated, so rearrangement can occur in order to stabilize that carbocation. So also, as you see, since the carbocation is generated, so alkyl halides having touch, the order of the alkyl halides forming, doing this even mechanism will follow the trend tertiary, secondary and primary, because tertiary alkyl halide will generate a tertiary carbocation which will be more stable. That's why the order of alkyl halide performing this even mechanism will follow this trend. And again, the since the formation of carbocation, so it is also favored by protic solvents. Okay, now let us do one more example. Let's say we have, now I'll discuss one with the substitution, with the possibility of rearrangement. So you have H over here, H over here, CH3, C, let's say CH3 over here, H over here, H and X. So in the first step, what will happen? Removal of halide, the removal of the leaving group. This X leaves minus X. Okay, this X is leaving. What will generate? A carbocation will generate. Now this is a primary carbocation. Can you see the possibility of rearrangement? If we perform the rearrangement over here, 1 to hydrogen shift, if we see if this hydrogen goes to this carbon, and then what kind of carbocation will be having? CH3, CH3. The positive charge will form over here. CHH. Now, the generated carbocation is a tertiary carbocation. So, out of the two, the primary and the secondary, which you think is more stable? As you can see, here is only primary carbocation, and the other one generated after rearrangement is tertiary carbocation. So, rather than the attack of the nucleophilic base on this primary carbocation, reaction will happen with the tertiary carbocation. Rearrangement will happen. Now, in the step 2, attack of nucleophilic base. That will abstract the proton from the alpha position. So we have this tertiary carbocation CH, H and H. Now this is the alpha carbon nucleophilic base. Let's say B for understanding B minus. This will abstract this proton and the two electrons from the CH bond will come to this carbon and will generate a pi bond CH3 double bond CH. This is the product that you will get because there was the possibility of a rearrangement of the intermediate generated. Now we'll move to the second type of elimination reaction, that is E2. Why we call it E2? Because in the case of E2, what happens? It is a second order elimination reaction similar to the SN2 where nucleophilic substitution was happening. But in the case of E2 elimination, what happens? E2, it is a single step elimination reaction, single step process. Rate dependent on rate depends upon the concentration of alkyl halide plus nucleophilic base which is reacting. Third point is single transition state. In the case of E1, you saw the formation of carbocation, but intermediate carbocation was forming. But in the case of E2, transition state is generated, okay, with no intermediate. Since transition state is generated, so are no possibility of rearrangement. Strong base generally perform E2 kind of reaction mechanism. Strong base are generally used, and order of stability is followed as tertiary, secondary, and primary for the alkyl halides. As in number of alpha hydrogen will increase as we go from higher to lower alkene, leading to alkene stability. Why this tertiary and secondary and primary alkyl halides under because in the case of E1, you saw if tertiary alkyl halide is there, then the carbocation will be more stabilized. But why, if we are in the case of E2, this is a trend. This is a trend because ultimately you are generating, since the X and Y group will leave and you will generate an alkene. So if these are the bulk R groups are present over here, let's say tertiary alkyl halides are there, so there will be more stable alkene generated. So stability of the product matter here. Stability of product matters. While in the case of the previous one, you saw that stability of the carbocation was favoring. That's why the trend was tertiary, secondary, and primary. But here the stability of the alkyl halide is important. So also, since there is no formation of carbocation or intermediate, it is mostly favored by aprotic solvents. Let us discuss example. What you understand till now, I am trying to make you understand that in the case of E2, it is a single step process where Let's say you have this alkyl halide H, R1, R2, R3, R4 and X. What will happen? A stronger base will come. It will abstract this proton first. The two electrons from here will go and make the double bond, and the X will leave as the electron density of this CH bond will come over here. So the X will leave, leading to the formation of alkene. So what is happening? The this R1 and R2 are here. A double bond is formed. R3 and R4 are here, and base has abstracted that proton, and X minus is released. So you can see it is a one-step process. No intermediate generated, only one transition state. Rather, transition state is there where the simultaneous attack of the base on the alpha proton and the removal of this leaving group happens simultaneously. Rate is dependent on both the alkyl halide concentration and the nucleophilic base attacking, and there is a trans elimination. Trans elimination, by trans elimination, what I am trying to say, that the hydrogen removed is trans to the alkyl halide. The halogen of the alkyl halide base abstracted that proton which is trans, so that there this H release and the electron density shifts over there, which release the halogen present in the trans position. So you will understand all these factors in brief in upper classes. So far now, if you see, I was talking about the stability of the product affecting E2. So if you have an alkyl halide, let's say you have CH3 over here, you have H, you have H, you have two hydrogens over here, and you have like one bromide. You have one this reaction, and in other one you have H, CH3, C2H5, single bond C, CH3, C2H5, and like bromide over here. Now in both the cases, if you say one nucleophilic base is coming, this base will abstract this proton, the electron density will move in the middle of the two carbons, and the bromide will leave. The kind of alkene product that will get over here is the CH3 over here, the hydrogen, carbon, carbon, double bond in between, then you have two hydrogens. So this is the alkene product we got in the first one. If in the second case the base abstracts this proton, the electron density from the CH bond will go over here and the bromide leaves. Then you will be getting this C2H5 carbon CH3 double bond, this CH3 and C2H5. So out of the two, please tell me which one is more stable alkene. Obviously, the board substituted one is more stable. That's why the alkyl halides having tertiary, secondary, and primary order. In this order, the stability of the product is in more. Therefore, it undergoes more faster than E2 elimination mechanism. Now we'll come to the third one, which is elimination via conjugate base formation, E1CB. Third type of elimination reaction, which is E1CB. In the case of E1 mechanism, you saw the formation of intermediate, that is carbocation was forming. In the case of second one, E2, you saw the formation of this was no formation of this carbocation, rather a transition state it was there, where the simultaneous addition, simultaneous removal of the proton and the leaving group was happened simultaneously, leading to the formation of alkene. While in the case of E1CB, what happens, it is a two-step process, again two-step process similar to E1, but here what the first happens in the first step, there is formation of carboanion forms. How carboanion forms? Because H is released first. Base abstracts the proton first. Release from the attack of base. And the generated carboanion is generated as an intermediate. And then the second step, leaving group leaves. Two step, there is step 1, this is step 2. So this generally even CB happens when poor leaving groups are present. So let me explain what happens in the reaction. So you have this alkyl halide H and X is present over here. So in the first step, there is this one is the first step, loss of proton via nucleophilic base. Okay, so the base over here will abstract this proton and will take this and will generate a carbanion. You will be generating carbanion over here. After the generation of the carbanion, what happens in the step 2? The generated carbanion delivers its electron density over the bond between carbon and the X, which is a poor leaving group, is now released. So this one is the slow step. What happens? Plus X minus. So this is what happens in the even CB rather than the formation of carbocation as compared to the even mechanism. In even CB, there is first loss of the proton by the nucleophilic base, which generates the carbanion, and the carbanion then formed leads to the formation of nucleophile. So here also there are possibility of rearrangement because of the carbanion generated. So let us take one more example. Let's say you have this C double bond O, C, CH, and CX over here, R, 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 let's say R, R, and R. So what will happen if some base is a nucleophilic base is there, it will abstract this proton and there is formation of carbanion. So carbanion will be generated on this carbon next to the carbon where halide is present. So stability of carbanion again matters over here. If you can see the double bond present in the carbon next to this carbanion is basically stabilizing this carbanion. The double bond over here can undergo resonance and the stability is increased. So this one is a more stable carbanion. What will happen next? In the step 2, this carbanion will undergo transfer its electron density so as to remove the halide present in the alpha carbon position. It will deliver its electron density between the C double bond C and the X will be released. So with the product that you are left with is C double bond CR, CR leading to C. This is the product that you will get. So far now what we understood that summary for the today's video, we understood the alkyl halides are derived from from alkanes. Okay, so on the basis of the carbon, on the basis of the carbon to which halide is attached, we can classify alkyl halides into three categories as primary, secondary, and tertiary. Primary alkyl halide is the one where halide is attached to a primary carbocation. Secondary alkyl halide is the one where halide is attached to a secondary carbon. Tertiary alkyl halide is the one where the halide is attached to a tertiary carbon. Then we move to the types of reactions in organic chemistry. So, what we discuss, type of reactions, we discuss addition reaction, substitution reaction, and we discuss elimination reaction. Briefly, we discuss addition reaction. What happens to a double bond? A group will attach and this will lead to a saturated carbon alkyl halide. This alkyl halide will attach and there will be addition reaction like this. In the case of substitution reaction, what will happen? Incoming nucleophile, let's say this there is X and this is chloride, incoming nucleophile will come and replace this X and there will be formation of a new alkyl halide, uh, like Cl will be there and X will be released. In the case of elimination reaction, what happens that initially there is an alkyl halide like this. Uh, this will undergo elimination to generate a double bond alkene along with the removal of this leaving group X and the alpha hydrogen present next to it. So we also discuss the further types of substitution reaction. Substitution reaction involves SN1 and SN2. SN1 is basically a two-step process where there is formation of intermediate called carbocation. Carbocation generates whereas SN2 is one-step process and there is formation of transition state in here. While in the case of elimination reaction, we discussed that elimination reaction of it could be of three types: E1, E2, and E1 CV. In case of E1, two-step. In case of E1, one-step process. E1 CV is also two-step process. Here carbocation generates. Here transition state forms. Here carbanion forms. So we have discussed all this in brief. We'll discuss further about the mm, more about these reactions in the next video. So goodbye and thanks for watching.